Hi everyone. In this section we're going to examine some basic characteristics of MOSFET and get to a feel of how it works and some important concepts about these devices. So first let's make sure we know how to put a MOSFET into a circuit diagram. So let's just look at the circuit symbol that we would use. So I'm drawing the symbol for a N-channel enhancement mode. So the primary three terminals are the source, gate, and drain, and then we can also later on in the discussion talk about another channel, the body, which can also be used to adjust the threshold voltage of the device. So you'll notice that the source and drain are not connected in this diagram, and that's because this device is normally off. And that is, we have to apply a gate voltage a positive gate voltage in order to turn this on. We can change it to a depletion mode device by changing the direction of voltage, or we can change the work functions or doping in the material to achieve this. So the circuit symbol for a depletion mode device would have a connected line between the source and drain, and instead of being normally off, this will be normally on, and that's sort of what's the idea shown in the connected line. So the basic idea that we use to analyze the MOSFET is that the current between the source and the drain is given by a quantity which we'll find out a little more about, but called the transinductance, excuse me. And this turns out to be a function of the V-gate especially, but also the source drain voltage when we look in more detail. And then the current flowing is primarily proportional to the drain source voltage. So in a sense, we've just written down Ohm's law, like current equals 1 over resistance times voltage, and the voltage is the source drain voltage. So let's just make sure we draw a little schematic of the device. So we have our source, our drain, and our gate. And the transconductance G is going to be the sort of connection between the source and drain in terms of current flow. So it turns out that in an enhancement mode device, especially, we can consider the sheet charge that's generated at that interface between the oxide and the semiconductor to be the thing that controls the conductance. And so we can write that the G, the transconductance, is some function of geometric variables, the width times the length, and on this picture the length L is the distance between the source and the drain, and then you can imagine the device going back into the page here and so width would be the dimension going that way. We have the mobility in the channel, and this of course is going to depend on the E field present there, as well as scattering mechanisms, roughness of the channel, and other factors of fabrication. And finally, we get to that quantity I alluded to, the charge in the inversion channel. Okay, so let's investigate what happens to the charge in the channel as a function of gate voltage. So first, let's look at what we're going to plot. We're going to put this versus V gate, and we're going to plot the logarithm of Q here, and basically the plot should be linear for as long as we have a small drain source voltage. So the level at which the transistor turns on is going to be when the n-type electron charges equal the p-type doping. So let's say this is the point where it turns on here at threshold, and we're going to say that the number of electrons here equals the number of holes, and so it turns into the inverted state. So the slope of this curve here is something that's important to note. The ability to invert the channel very easily with small increments of voltage is desirable. Or another way of saying that is, it takes a little bit of voltage to turn the transistor on and off. And so we define the slope here would be given as, so this is going to be given as the dq dv, and we want this slope to be as steep as possible. Later, when we talk about the current, we actually want to discuss the inverse of this slope, called the subthreshold swing, and that's an important metric for how fast you can turn on and off devices, and how easily you can do so with small voltages. So we've established that we can exponentially increase the charge in the channel with the application of gate voltage, and so the current, remember, is proportional. The current between the source and drain is proportional to this charge, and so we can now look at a plot of the current versus drain source voltage, and then look at different curves for different gate voltages. So now we're going to plot the drain source current versus drain source voltage, and for gate voltages below the threshold, we basically get the transistor off, and I'm just drawing it slightly non-zero just to indicate that there's leakage. So V gate less than V threshold, and then above threshold we see this current pop up, and as we continue to increase the voltage, we see an increase of the slope in the region before it flattens out, and then a flattening out behavior. So there's two regimes here. We call this saturation, so just to avoid confusion, the threshold voltage goes with V gate, and saturation goes with V drain source. And these curves I've drawn, we're increasing V gate going this way. So you'll notice two things. One, the saturation current is larger as V gate gets larger. So another way of saying that is the transconductance has gotten larger, and thus for a given drain source voltage you get more current. And then also the slope of the slope of the region before saturation also increases. Okay, so in the linear region below saturation, we can sort of treat the behavior one way, and then at saturation we treat the current with another set of formulas. So let's take a look at those first. So the formula for the pre-saturation region is here. So we have some geometric factors, the mobility, and then the oxide capacitance comes in, and then we have some functions of voltage here. So first we have the gate voltage minus threshold, so sort of the reduced gate voltage above threshold, times the drain source voltage, and then minus VDS squared. So this is for VDS less than VDS sat. And then above saturation, we can make another formula. So let's look at the condition for saturation first, and one way to do that is to sort of analyze the transistor in a little more detail than I want to go into here, but the result is that VDS sat equals VGS minus VT. And you can look at this equation above and actually maximize that equation by taking the derivative and then setting it equal to 0 and so on, and you'll arrive at this result. So if we make that substitution back in and get the saturation voltage, we'll get the expression below. So we end up with W over 2L mu Cox and then when we substitute back in, we just get VGS minus VT quantity squared. and this again refers to the maximum point where it just goes to saturation. Having a little trouble drawing with the pen here. There we go. Okay, so when you characterize the performance of MOSFETs, these are the two equations to use above and below the saturation voltage in terms of the drain source voltage. So why, we may ask, does this thing saturate? That's a great question. We're gonna give a very sort of simple, intuitive picture to carry around in our heads. The idea, and the book by Neiman actually goes into a derivation here that's a little more advanced. The idea is that we've got our source and drain, and our channel, and when we start applying, and sorry, here's our gate too. So we're going to keep the gate voltage fixed and sort of turn up the source drain voltage. So we've applied enough gate voltage to establish a channel, an inversion layer here, and we're going to think about what's going to happen as we turn up the source drain voltage. So what's going to happen is basically the potential from the gate will interact with the potential from the drain. Basically, one voltage is going in the x direction, the other is going in the y direction, and it turns out that as you keep increasing the drain source voltage, you'll eventually I'm going to change the color here. So you'll eventually reach a point where the inversion charge goes to 0 right at the edge of the drain. So as we superimpose VDS on V gate, and remember that in a resistive channel, the voltage drop will be linear from the source to the drain. So we can kind of imagine that the superimposed total potential at any point is decreasing linearly that way too. So when it so-called pinches off the channel, the net result is that it no longer matters it no longer really matters to the electrons that you're increasing the source drain voltage. They still have to face the same sort of picture, an easy transport through the inverted channel, and then sort of higher resistance or lower conductance transport in the region that's no longer inverted. So basically where it rolls over is the point for each gate voltage where we create that pinch-off point. Okay, so now that we've established the basic shape of the current versus, the source drain current versus source drain voltage curves, and we've motivated why the saturation happens, let's look quickly at how to find the different quantities for the device. So first, let's look at how to find threshold. So in order to determine the threshold voltage, we actually want to plot the I source drain versus gate voltage. So this is different than the plots we've been making. And basically, you're going to have a region where it's linear, and what you do is draw a straight line through that region down to 0 and call this your threshold. Of course, the transition, there's no such thing as zero current running through the device as long as you have a finite drain source. There's always going to be some leakage, and so you have to sort of do an extrapolation plot to determine this. So the slope here is from our previous equations. In the small source drain voltage regime, the slope is di source drain versus dVGS, and this equals the width, oxide capacitance, the mobility over 2L, and then times the source drain voltage times VGS minus V threshold times, VDS. So we've just done some simplification there. Okay, so in the saturation regime, the current depends slightly differently. So VDS greater than VDS sat. You end up plotting the square root of the current. And when you do that versus the gate source, so let me draw a dividing line here. ISD square rooted V gate. So now you can also find a linear behavior between these, and again that will extrapolate down to V threshold. So in the two different regimes, below saturation and above saturation, you can make two different plots to find the threshold. And the let me complete that. So the slope is given by the square root of mu Cox W over 2L. So in either case, you should be able to determine some of the parameters. Now, you'll notice that in either case, above or below saturation, most of these parameters are geometric, and the mobility is the one that is kind of most sensitive to material quality, and so either of these can be used to find the channel mobility in either below or above saturation. Okay, so let's look at two other definitions. So the transconductance G, this is Di versus dV VGS, the slopes that we were just looking at, the slope we were looking at below threshold. And again, the transconductance is what this quantity is called. And remember, if we go back to our definition, we have G times V gate source. The next thing I want to talk about is the subthreshold swing, or the subthreshold slope. So we started to at least mention this previously, but what you do is plot versus V gate source. You plot on a log scale. So previously we plotted on a linear scale. It took a extrapolation to find V threshold. Now if we go on a linear scale and look at the region below V threshold, we'll have some region where this is linear. So let's just draw VT here, and just note that we're sort of to the left of the region we discussed before. So on this plot, the slope we want the slope to be as large as possible, meaning that we can change the current by 1 decade with the smallest possible voltage. And it turns out that the theoretical smallest number you can hit is about 60 millivolts needed to move 1 decade. So, and that comes from the natural logarithm of 10, which converts you between ln and log base 10, and then times the thermal voltage. And in the next chapter, we'll see where this comes from when we discuss the subthreshold leakage current or subthreshold conductivity. We'll physically discuss this, but the number that you're looking for if you're trying to make the best MOSFET possible will be to push that subthreshold swing, which is 1 over the slope, towards this 60 millivolts per decade. So again, the swing is given in voltage per decade of current. The slope of this plot over here that we made obviously is in decades per volts. Okay, the last thing to discuss is the effect of biasing that body. So let's draw our structure again. We've got our gate, our source, and our drain, and this is the body here. So what we can do is sort of add to the gate voltage in a sense. So the body voltage sometimes called base voltage too. It sort of adds to the V gate, but excuse me, let me erase that. We're no longer assuming that we're grounding it. So it's not quite the same effects because it's changing the relationship between the source and the base now. Previously we were assuming that they were both grounded. So the main effect is that it's going to change the threshold voltage around. So if we plot the V gate source and versus square root of the current, so this is in the saturation regime. What we'll see is a family of curves. So this is the original V threshold, and if we apply a positive body voltage, so this is 0, VB greater than 0, we'll change the threshold voltage. And that threshold voltage change is derived in the book and given by this formula here. So square root of 2 times the electron charge times the dielectric constant of the semiconductor times the doping. So basically this form tells you that it has something to do with the depletion width changing over C aux, and then times the quantity that I'm going to move down in brackets here, square root 2 phi fp plus V V base minus square root of 2 phi fp. Okay, so what you can do is get a little more control over your channel charge by using that fourth terminal, that base, to sort of add and accentuate the effects of the gate. Alright, so we've in these two videos here, we've gone through and sort of seen the basic current voltage curves of the MOSFET. We've looked at sort of phenomenology and looked at the equations that govern the source drain current as a function of source drain voltage. We've seen how the gate voltage affects things in terms of changing that channel charge and moving you above and below threshold to turn the device on or off. We've also added this new concept of saturation, where the source drain current rolls over and becomes constant because of the pinch off in the channel. Then we've looked at the transconductance to find it, also the so-called sub-threshold swing to find that, and then lastly looked at the effects of using the fourth terminal, the backside or body voltage that you can apply to the wafer itself to sort of help the gate do its job.